So let's look at our first problem here. And we're going to take a look at, with rotational systems, handling things in series. I have two of them. So here's the first. So the idea here is I have two rotational springs. They're connected here. So what we did before in translational systems, we'll consider there to be a virtual inertia here, except it's zero. So we just treat this as a mass point, this node. Here I have my flywheel inertia. So we're measuring theta 1 here, theta 2 there. There's a torque applied. And so as this torque is applied, it's being opposed by this damping in that spring. So when we do this, if we had push-pull before, we have twist-turn now in terms of how to do it. So what that means is, which one do I want to start with? That one. When I want to figure out what's going here, I'll hold this position still, give this a twist, this inertia, and say, what does it feel? And then afterwards, I'll hold this still and give this a twist in the positive direction, which would be, I'll assume, looking this way, counterclockwise. But I'll give this a twist and go, what does that feel? Then I will focus on summing the inertias here. Of course, the inertia is zero, but that's okay. And then I'll say, okay, hold this still, twist that, what does this feel? And then I'll hold this still and twist that and say, again, what does it feel as a result? So starting here, what do we have? If I hold this still and twist this in a positive direction, it's going to feel opposition due to the damping in K1. So I have a minus K1 theta dot and a minus B theta 1, minus K1 theta 1 and a minus B theta 1 dot. I may have said that wrong. All right. And then you hold this still and turn this in a positive direction. And so then that movement of K1 theta 2 will be a torque in the positive direction here. So we see that there. And then, of course, we have our input torque, which you can't really, from the picture, you can't tell what it's doing, but we'll take it in a counterclockwise positive direction. So there's that equation. Then we go down here. So this would be nominally, say, J2 theta 2 dot, double dot, but that inertia is zero, so that just zeroes that out. So we say if I hold this still and I twist this in the positive direction through that spring, I will have plus K1 theta 1. There you go. And then if I hold this still and turn this in a positive direction, K1 and K2 will oppose me. So minus K1 theta 2 and minus K2 theta 2. The minus is inside there. And that one's all done. So the next one, we have a torque applied here, which we'll take to be in the positive direction. We have 1, 2, 3 inertia points we need to model, except inertia here will again be zero because it's massless. All right, I'll take that to be counterclockwise positive, and we do the same thing. So let's see, where did I start? So for J1, we twist this in a positive direction and say, what does it feel? Well, there's a positive torque applied. Okay, and as I twist this, this will oppose me. So it'll be a minus B theta 1 dot. And if we look here, here's the torque, and I have my minus B theta 1 dot showing up right there. Okay, then I hold this still and turn theta 2 in a positive direction, and so there will be a twist applied here due to that damper, plus B theta 2 dot. So now I got to model the middle piece. There's no inertia, so the zero goes there. And so we can say, okay, twist J1, what does it feel? That would tend to take that in a positive direction, B theta 1 dot. Okay, if I hold that still, hold this still, turn this one, then that would be K theta 3 driving that forward, counterclockwise positive. And then I'll hold these two still, turn this one positive, and it'll have opposition B theta 2 dot, and it'll have opposition, if I take this and spin it, K theta 2. And so here we have minus K theta 2 and minus B theta 2 dot. That takes us to the third one. So if we hold this still, turn this in a positive direction, we have a minus k theta 3. And you can see that right in there. Okay. And then if we hold that still and take that in a positive direction, it would be k theta 2, taking it counterclockwise. And there those are. All right. And excuse me while I make a quick decision. Yeah, I'll do another one real quick. So here we have a pendulum, classic pendulum problem. And so we have a massless rod here. So that would have no inertia, but we got a mass at m. So inertia would be mr squared. So you can recall the parallel axis theorem where that would come from. I have a counterclockwise positive torque being applied to this system. We have damping basically in the bearing here where this rotates. So that would be b theta as that goes. And so if we model this, here's our j, theta double dot. And so as this goes, this will oppose b theta dot negative. And also there will be a torque due to gravity. So picture we have mg coming down. So mg and then r sine theta, this horizontal distance, would be the moment arm of the torque. So here we have minus b theta dot and mg r sine theta, plus the torque that's applied. Now, if you do a Taylor series expansion, which I don't expect you to do right now, but I'll just note, for very small theta here, sine of theta is roughly equal to theta. All right? And so if you make that substitution for sine theta, now you have, this is a nonlinear differential equation. Now it's linear. Mr squared theta double dot is bringing stuff to the other side. B theta dot plus mg. I put L here. I was calling this distance R here. So I need to make a little change there. I'll do that in a moment. Equals the torque applied. So it's just summing torques. Very straightforward. And I will end this lecture at this point. Talk to you soon.